talk about the ASTM D2435 standard test method for 1D consolidations properties of soils using incremental loading, particularly for consequent constructions and the log time and square time method for soil parameters characterizations after we have the consolidation data. So here first, here is a ELOC curve, and we need this curve to perform the consequent constructions. On the y-axis now is already is in the form of Boyd ratios. So we have already gone through the data processing, converting the Dow gauge data to Boyd ratios. And the x-axis the stresses, and it is on a log scale. So this is a semi-log graph. And if we walk through this curve correctly, we can identify that's the kind of like a three portions or three general slope or the regions of the graph to depict the soil behavior. First, it start with the linear part of the test. So you would imagine the graph start with a linear portions of it. So that's like what we call the V compression part. And then the slope change quite a bit with a greater slope. This is the V compression part. Sorry, this is the compression part. So start with the V compression part. Then we have the compression parts, or we call the divergence compression regions. And then we do the unloading. So sometimes this is optional. So if your test didn't go through a unloading procedure, then you don't have this part of the data though. So the test stop at whatever highest load or highest like vertical stress you put on the soil specimens. And if you have it, you have a V bump. So that is the another V compression part. And periodically, like the slope, the V bump here, the left should be same as what we have on the V compression strength in the field. And the breaking point or the change of the slope to the locations where you change from the recompressions to the compressions, typically that is your maximum pass pressure. So now we have this curve on the engineering procedure. Tell us what to do is first we identify the greater points of curvature. So if we put a straight edge, keep stretching, whereas the change of the slope give you the greatest curvature points again, which is like the point where it gives you the greatest slope when you feed like a tangent line along the curve, and that is the maximum curvature point. And once you identify it, for this example here, draw a tangent line, and again this tangent line should give you the greatest slope of all the tangents when you try to fit through this curve here. Next, you will draw a horizontal line to that particular point. Then you will bisect the two lines that we previously mentioned. So which is the green line here. So the green line here should give you two equal angles, upper and lower, to the two lines that previously established. So after that, we mentioned about the virgin compression part, which is the compression line here, the black line. So we extend the slope for this part of data to the top, and wherever it meets with the previously the bisections line, the green line here. So again, whereas in this case, the black and the green line meeting, that is our maximum pass pressure. That is our maximum pass pressure. So that's how we try to identify the maximum pass pressure per the ASTM standard using the consequent constructions. And you may ask, why we need to do it? Why don't we just pick the maximum coverage point, like the red circle point here? as our maximum pass pressure, which is a little bit less than what we have done like on all those graphical procedure. Like, we may be reading like, a couple decimal points of tons per square feet here. But you do see, especially the x-axis in the log scale, you to see to realize the change in magnitudes in terms of like this maximum corrosion point versus the intersections point that we create per the engine procedure. Why we need to do that? So the main reasons behind is because we want to correct for the solid disturbance. Again, like if we perform our consolidations or dominant tests right on the field without any disturbance, we should get like a perfectly bilinear behavior on this log P curve. For example, this blue curve right here, and with a really clear breaking point, and that breaking point theoretically in a perfect world, that is a maximum pass pressure. But in our actual scenario, actual world that we live on, it's not perfect. Once we try to collect soil samples from the ground, we release all the stresses, and from the transportations from the site back to the lab, there could be loss of moisture and many other things, man-made activities will from the soil collects process will create this disturbance, and the disturbance will reflect in the ELP curve. And if we have extreme case, for example, like we take our soil samples back to the lab, we totally like we mold it, we dry it out, and then we put it into powder, and then we reconstruct it with the powder, the clay powder, and mix it with water again, and then put all the stresses. So if the soil samples is totally removed and reconstruct again, we do consolidation test, we get a smooth curve. So that is like another like opposite to the truly bilinear and disturbance behavior that we would expect for soil residuals, how we react. And if we collect disturbance samples from the site, to substitute the degree of the care that we have, the better contractor and the better care that we have, we will get a curve that more close to the undisturbed behavior here, the bilinear behavior here. But if like there's a lot of soil disturbance, then we get close to the remote curve here. So the fact is, once we collect the soil samples, we don't know the disturbance, or we know that the line that we get, the curve that we get, even though we pick the maximum corridor point, it's not the true answer, because the true answer is somewhere should be a third right. So if we just pick the maximum corridor point, we are underestimating the maximum pass pressure. So that's why the Kazakh the procedure provide us a simple yet effective engineering graphic tool for us to correct the soil disturbance. So we can more effectively to estimate the maximum pass pressure from our odometer test data on the ELP curve. Okay, next, we also need to find out other parameters for the compression index, C sub C, and also recompression index, C sub R. And sometimes it's called as the C sub S, the swelling index. So again, as I mentioned, there's like 3 regions on this ELP curve, and the 2 of them, the green, the recompressions and the rebound part represent the recovery of the soil samples in terms of repeating the loading that it has already been experienced, like either like being recompressions and rebound, you already like past the previous maximum pass pressure. So they should behave on this ELP curve being like a parallel. So you see the upper green and the lower green theoretically they should be the two lines that being parallel with each other. So this two lines again, they should be parallel with each other. And you may ask, like, if these two being parallel with each other, which one you should pick to calculate the slope such that you get the C sub R, the recompression index? The answer is you should get the lower portion one if it is available, because this rebound one, you have already mimic the create the maximum pass pressure in the lab. So in that sense, you erase any soil disturbance that you may have from the top. As you can tell from the top, you're not quite sure where is actually the maximum pass pressure. So you need the quantity constructions to help you to better estimate it. And you may have a little bit hard time to determine like what how to draw this like a green slope right here, because the data here is a bit messy without like the erase of the disturbance. The other thing we do in the lab is, since this go beyond the maximum pass pressure, so you have to erase the disturbance that like the soil has. And once you pass the maximum pass pressure in the lab, you're kind of creating a new fabric structure without any disturbance, because you're right on the spot on the odometers, having the new soil structure. And in that case, so that's why the lower portion is more reliable in calculating the C sub R. So whenever possible, if the rebound data is available, first of all, if you can order it, if you can do it in the lab, it's highly recommended to do that. And second is once it is available, then that's the preferred data for you to calculate the C sub R, the recompression index. And for both C sub C and C sub R, since they in a semi-log scale, so you need to take care of the log scales on the denominator here when you calculate the two index.
So let's talk about the log time method. This part is for finding the parameters of C sub V, the coefficients of consolidations. Per the ASTM method, there's two approaches. First is the log time method. The other one is square root time method. I will talk about each of them. And first, this is the log time method, and which require the data, the time settlements data, to be plotted as a log scales on the x-axis on the time, and the y-axis we are seeing here in normal scales. This is the corrected dial gauge reading. And from this curve, we're roughly seeing three three regions over here. First, we have kind of like a first slope on the soils deforming at a slower rate, and then you accelerate, so you see the slope getting larger, and then you were being slow again. So again, there's a three region right there. And first, the log time method, the procedure requires us to identify one point from the curve, and the requirement is that when we pick this point, it needs to be within about 1/4 to 1/2 of the total settlements. What it means is, when you look at the y-axis, for example here, the total settlements is about, for this particular stress level, is about a 0.265, and it starts at about the reading of 0.2 for the stress level. So half of it is one here. So pretty much like you go to your y-axis, look at the midpoint, and also the midpoint of the first regions, first half, like right there. So this point here represent like 1/4 of the total, roughly about 1/4 of the total settlements. So between this line of 1/4 and this line of 1/2 of the total settlements at this particular stress level, we can pick any points. So here I pick this point right there, and from there we can start our engineering procedure. First, we read the time for this particular point. We divided this time by 4 times, and then we can read the corresponding settlements for those 2 times right there, T1 and T2. We know the difference between the corresponding settlement readings, S1 and S2, and we go up at the equals amount of distance, and we go back to our y-axis, and we get what we call this S0. S0 means the settlements at 0% consolidations at this particular stress level. Again, like whenever we increase the loading, then the consolidation process got reinitiate, and every time we have a new set of water being pushed out, so this S0 will be restart again if we increase the loading or at another stress level. So that's why we have so many of this plot for your lab exercise, because we have 12 to 14 loading increments. So each loading increments you would expect one time settlement curve and go through all this procedure we are talking here. End up you have a specific loading specific C sub V values. So here we got the S0, right? And then next, what we do is we extend the middle part. We mentioned that we have like 3 different region right there, and the middle regions have the greatest slope. Now we extend the slope, and also we extend the slope at the last part. So we have two lines over there. Whatever intersect, we call this to be S100 when we go back to the y-axis. So what is S100? Well, S100 means the settlements corresponding to 100% consolidations, which means like the water that able to push out have already been pushed out under this loading. And whatever settlements that you occur later on is not because of pushing out the water or squeezing out the water. It's something else. Could be deformations of the soil particles. Could be the deformations of the water or something else. It's not no longer the primary consolidations. So here we have this S100, and thus corresponding to, at this point, mark the end of the primary. So from there on, this is the secondary consolidations, and before that is the primary. And now we know the S100, and next what we find out is if we divide S0 and S100 by 2, and the midpoint we call S50, and so pretty much S50 is the midpoint between those two. And once we identify S50, this is what we really want to find out from this procedure is the T50. So we know S50, go back to our time settlement curve, and the corresponding time that we get is T50. And this T50 is essential because we need this T50 to go back to our Tosaki equations to find out the C sub V. The C sub V. So the T50 here is same as the T50 we find out from the engineering procedure, and then go back to this equations. And this equations, this factor over here, 0.197, is actually the time factor, the Torsaki time factor at 50% consolidations. So this time factor is corresponding to the T50. And what we need in order to find out the C sub V, what we need is the HDR, the drinkage path. And drinkage path means when we conduct our consolidation test, right? Since this is a double drinkage, because we have the porous stones on top and below our clay specimens right there, so this is a clay specimens, and the drinkage path, since it's double drinkage, so will be half of the specimen height. So this is our drinkage path that we need to find out. And beware, this drinkage path is a function of time and also stress level throughout the consolidation test, which means this drinkage path is constantly changing. The drinkage path could increase when the soil specimen is swelling, and it could decrease when there's like compressions happening. And the good news is we keep track with the change of the soil specimen height with a dial gauge on top of it. So whatever we read, provided that the readings on the y-axis here, you have already processed it, means you have already take care of the zero reference, zero the data, and also you have already take care of the machine deflections, and also you take care of the polarity. Get to the point that whatever on the y-axis here represent the final corrected data to truly represent the deformations throughout the test. So, for example, here in this case, the T50 at this given stress level is 0.23 inch, which means you keep monitor the test, you correct all the data, and then now you know that at that timing, the soils has shortened because it's positive. In geotech conventions, again, positive means going downward. So it has already been compressed by 0.23 inch. And you see, throughout this time settlement curve right there, this numbers keep changing. And at the particular moment, this is what we need. And so the drinkage path is equals to your original specimen height minus your reading as 50, and then divide by 2. And then you need that, go back to these equations. And with that, we can find out the C sub V. And also, the other thing is one additional information we can get out from this graph is the secondary consolidation coefficients, C sub alpha. So C sub alpha is the weight of the coefficients of consolidations as secondary consolidations. So pretty much it's take care of this part, which means we need to find out the slope right there. So this is the secondary consolidation coefficients. Okay, finally is the square root time method. So this procedure requires the time on the x-axis being plot or being like a process or calculated with square rooting the numbers. So whatever you see on x-axis here is the same data point we have previously, but instead of putting on a log scale, has already been square rooted. So this is so that's why the curve look very different now, but it is the same data as the previous example. Again, like we square root the time, so now we have a different shape of curve. Given that this is still the same data from the same stress level from the same consolidation test. So once we establish this curve, first thing, the procedure required we feed a straight line on the first part of the data. So you see there's a red dashed line here, and we can calculate the slope of this line. And whatever like we intersect on the y-axis now, the y-intersections we call S0. Again, S0 is the corresponding to the settlement at 0% consolidations. So we know the slope for the red line, which is the initial part. Then the procedure require increase the slope by 15%. So you see the green line here. And when this increase the slope, the green line here with 50%, with respect to the original one, when it intersect with our time settlements curve, the data curve here, the intersections we call S90. So S90 means 90% consolidations have already been happened, and the S90 is the settlements corresponding to that. So now we know S0 and S90. We divided that by 2, then we get S45 here. So again, S45 means the midpoint between S0 and S90. So once we identify S45, we go back to our data curve and go back to our time data there, which is the x-axis. Then we get T45. Be careful, like this T45 here actually is the square root of the value, right? So we need to square it, undo the square root, so we get back to the true T45. And once we get the T45 here, we go back to this equation, the Tersaki equation now, same as the previous one from the log time method, but now this time factor here changed a little bit, because this is no longer time factor at 50%. This is the T45, the time factor at 45% of consolidations. And we know the corresponding S45, and just like previously, like what we had done, try to find HDR. The drinkage path will be equals to the original height of the soil specimens minus the settlements at 45% consolidations, which we find here on the y-axis. Again, provided that your y-axis, the dial gauge reading has already been properly corrected. So we know this, and then this is a double drain gauge, so we need to divide the number we have by 2. With that, then we can find out the HDLs. And again, from the engineering procedure per the ASTM standard, when we establish the square root time curve, we identify the T45, and we know the time factor from Tersaki theories. Then we can find out the C sub V. The C sub V is the coefficients of consolidations. So now you may ask why we need 2 different methods, the log time or the square root time method. And you actually realize each method they have their own good and bads. And anyways, it make it to the ASTM standards. So that's why we require you to do both of them. But which one is being good and which one is being this has more advantage. Actually, they are more likely equally rated at some point. Because look at this, the square time method. What being good here now is when we look at those parameters, we are pretty sure about the S0. Because physically, you can draw a line, and then you have intersections right there. You have a good a robust and quite good confidence in getting these values again and again. Means from data to data, from test to test, from different stress level to stress level. So the square time method gives us a good estimations of the S0, but not quite good on the S90. The this this 15% increase of slope pretty much is empirical based data. That we get a 15% increase, and is that applied to all the different kind of soils? It's true that with a 15% increase of slope, you always get 90% of consolidations being done. Not quite sure. And versus the other method, the log time method. This one, actually, we are not quite sure about S0. From data to data, from test to test, from interpretations to interpretations, you realize this S0 sometimes maybe go way beyond for the first data point here, or sometimes you close to, or sometimes even go above or go a little bit below. So you are not quite sure about S0. But on the other hand, it just gives you some certainty on the S100, because you can clearly identify the point that mark the end of the primary consolidations at the beginning of the secondary. So we have more faith on this S100 for this method, but kind of trading off the S0. So either method has its own good and bad, and the ASTM standard requires to do both of them. So that's why, on your lab report, we need to complete both two methods. And thank you for your attentions on this videos, and hope to see you.